Okay, check, done, report quality, there's no error, no warning, things are okay. Models, we must select a turbulence model, okay. Hey epsilon, you can select realizable mental Lechner, okay. You can select this correlation with production limiter. Okay, this is the settings you should use. Materials, we should add materials here to this list. Blend database, water, liquids. Copy, now it's added. Water, liquid added. And the other fluids, fuel oil may be added. Fuel oil, liquid. Okay, that was mistakenly. But business has nothing to do. It must be used here. Cell zone conditions for volume, boundary conditions for surface. Inner fluid is water liquid. Outer fluid is fuel oil liquid. Okay, now air is not used anywhere. Therefore, from materials, we can erase air now. And for fluid, let's keep aluminum. I'll show where it will be used. If we modeled solid phase directly, then there would be a solid here. And aluminum would be assigned there. But we will notice solid as a thin surface, very thin surface. So inner, outer fuel oil. Okay, now boundary conditions. I can categorize it. Okay, velocity inlet. Let's keep velocity inlet. 0.5 meters per second. You can calculate velocity directly. You can calculate velocity. Pressure outlet, zero pressure. Actually, it is zero pressure relative to this operating pressure. Okay, we can specify gravity here, and orientation is that. So negative z direction. Gravity negative z minus 9.81. So this is gauge pressure above reference pressure. So real pressure is bit plus gauge pressure is the absolute pressure. So this is initial guess for velocity inlet. It will change. So if you can write this, you can write this, you can write this, you can write. The result will not change. But convergence may be difficult. So there is initial guess. Initial guess zero pressure. Inlet zero pressure outlet is typically okay for such kind of problems. And as I said, the interface, one side is that, one side of the interface, other side of the interface. As I said, those are different meshes. The same surface, but the meshes are not the same. So they are not talking. This kind of mesh is called non-conformal mesh. Non-conformal mesh. But the surfaces are the same. Okay? So we will create a mesh interface. It automatically creates, but we will erase that because it allows fluid to pass. No, this is wild. Fluid will not pass through this interface. It's just a coupled wall. So manual create. We can say interface coupled wall, and coupled wall matching in terms of area, surface area. So we select this and this. Now coupled wall is matching coupled wall is created. we come to boundary condition. Shadow and non-shadow. Shadow and non-shadow version. One side to another, one side to one fluid, shadows to another side of the wall. That's all. So because this wall has two sides. One side is cold fluid, one side is hot fluid. I don't know which one is which. It depends here. But they are the same. So you enter the same thing to here. Thermal coupled well, as I said, aluminum 2 millimeter thickness. Where 1 millimeter thickness wall. Wall thickness is 1 millimeter, okay. 1 millimeter wall thickness. The same applies to here. When you enter a value to shadow for thermal, non-shadow version will get it. So this is the interface. So physically it looks like 0 thickness, but we specify the thickness here so that in calculation of the fluid flow, it neglects wall thickness, but in heat transfer, it takes into account the thickness of the wall. And with non-conformal mesh is handled by interpolation. Okay, with interpolation, one data from one mesh is transmitted to data to another mesh. Other walls, you don't need to do anything. It's no slip wall, stationary wall, nothing to do. Heat flux 0, adiabatic. Everywhere is adiabatic outside. Heat flux 0. This side, heat flux 0. That's adiabatic wall, okay? Reference values, you don't need to do anything. Let's keep them as it is. First order. Let's keep this also. Now let's monitor mass flow rates and exit temperatures. By the way, we didn't specify inlet temperatures. Okay, we specified velocity, but inner is cold. 25 Celsius, okay. Outside is hot. 125 Celsius. 100 Celsius more. For thermal, okay. I specified thermal boundary conditions. You can specify it also in terms of Celsius. When you say Celsius, you say 25 Celsius cold fluid inlet, 125 Celsius hot fluid inlet. Mass flow rate. Mass flow rate at the outlet. Okay, per surface. Mass flows. GPO plot. It plots the results. And also mass weighted average. Total temperature outlet. Temperature. Total temperature. Temperature plus kinetic energy effect. So is total temperature is temperature plus velocity, resultant velocity over 2Cp. Okay. And outlets. Per surface. Temperature outlets. Total temperature is selected. And we will initialize the solution. Hybrid initialization, you can use that. No problem. Disable this from this residual from monitors. Okay, let's wait for the solution. For the exit, you don't need to specify temperature because exit temperature is the result. But if there is a backflow at the exit, reverse flow, then there would be a reverse flow warning. Here there is no reverse flow warning. If there was a reverse flow, you can specify reverse flow of temperature, but from that you don't need to specify temperatures to exit. That temperature is specified. Okay, I filled it. Now y coordinate 0 is the mid plane, y 0. So we can cut this domain and obtain y 0. Between y 0 isosurface, mesh, isosurface, the surface where some quantity is constant. For example, the surface where y quantity is 0. Y is 0 plane, let's say. Y0 plane, I can plot temperature. You see hot temperature and low temperature. There is little interaction in these two. You reduce velocity, then temperature difference can increase. Okay, but you need your velocity, of course. You can reduce pipe diameter. Here, I can't reduce pipe diameter. I make velocities 1/5 of the original values to increase temperature rise. Outside is hot fluid, inside is cold fluid. Don't forget. So iteration, that's an iterative solver. There are 5 equations. 1 continuity equation, 3 force equations, momentum equations, and 1 energy equation. Okay, 1 energy equation. Okay, I can start from the beginning. It's better that way. Start the solution from start with lowering net velocity. So continuity equation, 3 force equations, Marrash-Stokes equations, and 1 energy equation. 5 differential equations are used to determine the flow field. And these equations are solved iteratively. Also, there is turbulent kinetic energy and turbulent dissipation equations. In the next spring semester, I open a course named Computational Fluid Dynamics Technical Elective. In that course, I explain theory behind these concepts. Okay. So these residuals must reduce. If these residuals are 10 to the power minus infinity means, so if residuals are too low, it means that the equations are well satisfied. If residuals are high, equations are not satisfied. That means that's approximate solution. So I can reduce under relaxation factors to improve convergence, to reduce the residuals. And temperatures. Okay, I think it's converged. More or less, it's okay. Temperature distribution. Okay, for hot fluid, okay, hot fluid is more affected, cold fluid is less affected. Because Cp is high for the cold fluid, Cp of water is high. For example, if we reduce Cp of water, remember Cp reduces number of transfer units and effectiveness of the heat exchanger. For example, for water, if we reduce Cp to 1/10, for example, reduce Cp to 1/10, I reduce the Cp. Now let's solve and see what happens. water temperature will increase more. You see, water inlet was here and water exit was here. Water temperature increased, you see. We reduced Cp of water. Or we can reduce Cp even more for water, hypothetically. Not in reality, but hypothetically. That's a different material, let's assume. We divide Cp of water by 100. Now its temperature rise will be 100 times more. Water lower Cp, now its temperature rise increased. Now let me show. You see, water temperature increased greatly by reducing Cp of water. We can plot total temperature. It will be also the same. There's a small reverse flow here. Don't mind it. It's okay. Now let's retain original Cp of water. Okay, now water temperature distribution is like that. So how we will measure heat exchanger effectiveness? I will erase. I prepare the table. Okay, both inner pipe, water inlet, and water outlet. Cp of water is written here. Outer pipe, oil inlet, oil outlet. The Cp of oil is written here. To do that, we come to reports, surface integrals, mass weighted average. We select mass weighted average. Okay, temperature, total temperature. Inlet inner 25, 125. That's what we specified. Inner outlet temperature is less than 1 Celsius increase. It's not an effective heat exchanger, basically. And hot fluid enters at 125 Celsius. Now its temperature dropped by around 4 Celsius, more than 4 Celsius, because its Cp is lower. Cp is lower. It enters 25. It enters like that. And pressure loss, 2 or 3 for the hot flow, around 70, 69 Pascal enters. And outlet of the outer is this. So delta P, that's total pressure, remember, is minus this in terms of pascals. And Pascal. Is much higher less. Outer glass enters from here, goes from here and goes here. It has 60 Pascals pressure loss, cold flow, very low pressure loss, not so much. Effectiveness. First of all, Q dots heat flux. Heat flux is m dot Cp delta T. So we can obtain m dot from here, mass flow rate. For the cold side, mass flow rate is that. Mass flow rate for the cold side. That. For the hot side, this is the mass flow rate. Let's negatives are written, but hot side mass flow rate is more. Velocities are the same, but area is different. It's lower. Area is lower. Q dot transfer in terms of watts. Unit is watts. Here m dot kilograms per second. M dot times Cp times delta T. Delta T is minus this is amount of watts. M dot Cp delta T. Okay, they are not the same. You see that's numerical solver. So it's not converse well actually. This means that we need, so they are not exactly the same. They normally should be exactly the same. Minus code, let's make. They must be the same, MC delta T. So if you make more iterations, they will be equal, okay? They will be equal. Small differences will make them equal. So these heat fluxes will be equal. Let's do that. Let me try. Or this can take some time. Okay, let's assume that we did that. Heat flux is one of them. Effectiveness. Maximum possible. Two dots. Possible heat transfer. Called MCP, remember. Hot, MCP. Third one is that. This is minimum C, 96. So MCP, or we can say MCP, lower C, delta T max. Maximum temperature is between these two. This is maximum possible heat transfer. Heat transfer, heat exchanger effectiveness is this over this, or these two should be the same. 12.44%. Very low effectiveness, you see, because type parameter is too much here, or type parameter is too much, or velocities are too high relatively. That's pressure loss. You can calculate everything like that. Now, how to increase the effectiveness? Okay, reduce velocity to increase effectiveness. 0.01. 0.01. I'll initialize again. So just call percent heat exchanger effectiveness. You should also make this second order. I forgot to switch them for better accuracy. Okay, assume that it's converged. Normally it takes more RAM, but you can select coupled solver. Okay, coupled solver. You can have better conversions typically. Let's try. But in general, if you have 15 gigabytes RAM, then your mesh should be lower than 8 million. For safety, let's say 5 million is the top limit. If you have 8 gigabyte RAM, then your maximum mesh should be less than 3 millions. Okay? Okay, assume that it converged. Those are horizontal, no longer change with iteration. Mass flow rates. Mass flow rate is changing a bit, but let's assume that it's okay. So mass flow rates. Content. Of temperatures. Mass weighted average. For total pressures, let's write total pressures. .3 Pascal pressure loss because velocity is too low. Of course, once you increase this, it's not converged case. Net low pressure, so it's not converged. But maybe it was static. Only making it converged better would be fine. Minus Pascal. Strange. Low velocity. It's not converged well. Okay. That's very low velocity, so don't mind. But let's say temperatures. Heat transfers are too different. I think it's not converged well. Identity. We must wait more. Okay, we must do more iterations. Okay, anyhow, but if we will do these iterations, it will be as I did. Let's keep this, the old ones, with 0.1 meter per second. You can take pressure losses, and temperature rises with this way. Let's increase velocity. Very low velocities are difficult to solve. Let's keep the velocity. As you can include wood, for example, as the solid materials. Create edit and database from solid wood. You can increase wood. You can use wood material. Here wood. Aluminum, where was it used? In boundary conditions. In this shadow, you can take it in the shadow 1. Instead of aluminum, once you make it wood, 1 millimeter wood instead of aluminum. Non-shadow version will get the same thing now. You see? Other walls are adiabatic. Now initialize. Okay, let's make it as it in the original one. Let's make it default. Okay, I will write exit temperatures. Okay. Make it second order. Wood, so effectiveness will be even lower for the wood. Surface integrals, total temperature, mass rate average, inlet and outlet. And mass flow rates, let's check mass flow rates. They should be unchanged, 0.11. It didn't change, as you see, for the hot side. They are not the same. They should be the same normally. More iterations is required. More better conversions is required. Maybe final mesh. Heat transfers should match. Heat gain of the cold flow must be equal to heat loss of the hot flow. Okay. And it can be perhaps this reverse flow here. Here there's a reverse flow. Maybe it contributes to that. But okay, that can be fixed. So these two should be the same, for a much better tightness. 3% effectiveness. With human, 4% effectiveness. With wooden wall, 3% effectiveness. So effectiveness reduces with wood. What about surface heat transfer coefficient? I can also plot this. So this is interface version. Those are individual interfaces. We can plot it here. Well fluxes. Surface heat transfer coefficient. You see for one side, for another side. But heat transfer coefficient, T infinity should be written here. Reference values. Okay, you don't need to get this. For cold flow, you specify this because reference temperature is specified. Cold side, which one we can check, shadow or not. Not shown. Inner one, that's the cold one. Inner one is the cold one. So 25 because a reference temperature is required. T minus T infinity. T infinity is inlet temperature, 25 Celsius here. You can take that. That's a short exchange. Not shear stress, heat transfer for the inner side. A negative that shouldn't happen here. So it's not perfectly converged. So once we perfectly converge it, it will be better with the finer mesh. But heat transfer coefficient distribution for the inner flow. For the outer flow, inlet temperature is 125 Celsius. For the outer flow, surface heat transfer coefficient. So that was the inlet. There was an impingement. You can visualize the flow. So for cold outlet, you see there's some reverse flow. So here below there's some reverse flow. I'll make it transparent. So you can visualize the flow.